Okay, so in the first two chapters of your book, we've looked at different types of functions, linear functions, absolute values, quadratics. We found the zeros of quadratics. Now we're going to kind of expand on that and look at higher order functions, things like quadratics, cubics, quartics, quintics, and things like that. But in order to get there, we're going to start with looking at some quadratics again, but in kind of a different way than we're used to. Before, if we had a quadratic, we had something like this. F of x equals x squared plus 6x plus 4. And when we had that equation, our goal was to generally set it equal to 0, factor it, or throw it into the quadratic formula and get the zeros and be done with it. But now we've looked at transformations of graphs and how to shift graphs around. So there's another way to look at a quadratic, something like this. F of x equals x minus 2 squared plus 5. And I know from my rules of transformations that that's a quadratic. And let's see, minus 2 shifts me 2 to the right, 5 shifts me 5 up, and I can draw my vertex right there at 2, 5. And since the leading coefficient is positive, it's going to go up like that. And there's my graph right there. There's no reflections or anything like that. And we know how to do that using our rules of transformations. And the question is, can I take, say, that quadratic right there and graph it as quickly as I graphed the one when I knew the transformations? There is actually a trick to doing this, and I'm going to work through the algebra on this trick, and then we'll see a shortcut. And the idea is, when we solve quadratics, there's different tricks to solving a quadratic. One of them is called completing the square. And the way completing the square works is, if you don't know how to do it, you kind of isolate the quadratic term and the linear term. Then you make sure the coefficient of the quadratic term is 1, for this one it is. You take half of the linear term. Half of 6 is 3, and then you square that and you get 9. Whatever you get when you take half of that number and square it, in our case 9, you add it on. But from an algebraic perspective, if you add something to your equation, the only way to keep it equal is to immediately subtract that same number. So you're just adding 0. Now, I'm going to isolate the first 3 terms. That's a regular trinomial. I'm going to factor it. 2 numbers that multiply to 6, that multiply to 9 that add to 6, 3 and 3. So that's x plus 3 squared, minus 9 plus 4 is minus 5. But now I've taken a quadratic that looks like this, I've made it look like that, and now I can graph it. Plus 3 on the inside goes 3 left, minus 5 goes down 5, and I draw my quadratic, and I'm done. Which means, just using this trick of completing the square, we can take a quadratic that looks like this, change it to something that looks like this, and then immediately graph it. But I'm assuming you guys don't want to complete the square every single time. So thankfully there's a formula we can use. And the formula is this. If we want to find the vertex of a quadratic, the x value of the vertex is negative b over 2a. Meaning, if I have a quadratic, f of x equals x squared plus 4x plus 8. If I want to know where the vertex is, I can certainly complete the square. According to this, the x value of the vertex is negative of the b value, which is 4, all over 2 times the a value, the coefficient of x squared, which is 1. That's negative 4 over 2, which is negative 2. That gives me the x value of the vertex. If I want to find the y value, I just plug the x value into the function. And my y value, if I plug in negative 2, is negative 2 squared plus 4 times negative 2 plus 8. Let's see, that's 4. 4 times negative 2 is negative 8 plus 8. That cancels, and I get 4. So then, if I want to graph it, my vertex is at negative 2, positive 4. If I wanted to check that over here, just to make sure my trick worked, I can complete the square. If I complete the square, the coefficient of the quadratic term is 1, so I'm okay. So then I take half of the linear term, half of 4 is 2, square that, you get 4, and I add 4. But if I add 4, I immediately subtract 4, and then I do plus 8. Now I factor that part. Two numbers that multiply to 4 that add to 4, 2 and 2. So x plus 2 squared. 8 minus 4 is positive 4. This graph would be shifted 2 to the left, like ours, and up 4, like ours. There's no reflection, no negative, so it goes upwards. So from your perspective, if you want to complete the square every single time on a quadratic in order to find the vertex so you can graph it, you can do that. Or you have to remember this formula right here. The x value is negative b over 2a. Negative 4 over 2 times 1 in this case. As long as you have that, you can graph it. The only other trick is, and we're kind of glossing over this now, I found the vertex to be negative 2, 4, which is right here. Technically, the graph could have just as easily gone downwards like that. Finding the vertex doesn't say anything about whether it's a quadratic or a quadratic flipped. But if you think about it from a transformation perspective, right here, that determines if it flips or not. If it's negative, there's a reflection, which will flip it across the x-axis, which will make it go upside down. By the same token, all we have to do is look at the leading coefficient. If the leading coefficient is positive, there's no reflection, it'll open upwards. If there's a negative in front of the leading coefficient, it's a reflection, and it goes downwards. So, suppose we have f of x equals negative 3x squared plus 12x minus 5. I want to graph that. I can immediately say the x value is negative b, which is 12, all over 2 times a, which is negative 3. That's negative 12, 2 times negative 3 is negative 6. 2 negatives cancel, and that's 2. My y value is then negative 3 times 2 squared plus 12 times 2 minus 5. 2 squared is 4. 4 times negative 3 is negative 12. 12 times 2 is 24 minus 5. 24 minus 12 is 12. 12 minus 5 is 7. So my vertex is at 2, 7. So over 2, up 7. Then I want to know if it opens up or down. My leading coefficient is negative, which tells me there's a reflection. It opens downwards. And there's my graph. One thing to keep in mind, you can kind of mess around with this a little bit. We already know how to find the zeros. If my vertex is here and it opens down, I can see I have 2 zeros. I can just plug this into the quadratic formula, get the zeros, and then see if they match up with where they should go, and kind of get a bigger, fuller picture of my graph. I'm not going to do that because we've done that on other videos, but one other thing we want to look at are some applications. And there's lots of different applications for quadratics, but we're going to say this. I sell, we'll say anvils. Wile E. Coyote reference if you get it. I sell anvils. Our profit is given by P of x equals negative 100x squared plus 1000x minus 200. Where x is our price per anvil. Find the price that maximizes profit and find the max price. So, I sell anvils. Our profit is given by P of x equals negative 100x squared plus 1000x minus 200, where x is our price per anvil. Find the price that maximizes profit and find the max profit. I said profit and I wrote price. Okay. Well, if we think about it, if this is our profit, it's a quadratic, which means it's a parabola. The leading coefficient is negative, which means it's a parabola that opens downwards, which means the graph looks something like that. I want to find the price that maximizes profit and the max profit. That's clearly right there. But that's at the vertex. So just find the vertex. Let's see. X is negative b over 2a, which for us is negative 1,000. All over 2 times negative 100. 2 negatives cancel. That's 1,000 over 200, which is 5. Apparently our anvils are relatively cheap. If you've ever seen the Wile E. Coyote cartoons, that makes sense. So our price to maximize profit is 5. Our actual profit, we just plug in. Negative 100 times 5 squared plus 1,000 times 5 minus 200. 5 squared is 25. 25 times negative 100 is negative 2,500. 5 times 1,000 is 5,000. 5,000 minus 2,500 is 2,500. 2,500 minus 200 is 2,300. So then, what's the price that maximizes profit? $5. What is our max profit? 2,300. We're not a very good company selling our anvils to the Coyote. There are other applications you can do. I might make another video going through 1 or 2 applications of this. The one thing I would say though, from a certain perspective, these quadratic applications are the easiest ones you're going to see because there's only 2 things you can be asked. Either 1, find when something equals 0, find when a projectile equals 0, find when our profit equals 0. It's a quadratic. Set it equal to 0, factor out a quadratic formula. Or you're told to maximize something or minimize something. Once you're told to maximize or minimize a quadratic, you just find the vertex. Negative b over 2a, and you're done. So don't overthink these. Don't think you have to come up with some incredibly complex math to solve them. Either maximize or minimize, find the vertex, negative b over 2a. Or find when something hits the ground or when profit is 0, set it equal to 0, and solve.